Another really useful application of using a triple bottom line is looking at climate change. So climate change is something that we've had aggravatingly slow action on, and it's really only picked up now that we're seeing the dollars and cents costs in the global north countries. So this is an example of a really interesting study that looked at all these impacts of climate change and put them in dollar terms for a few different classes of impacts. So one thing that's interesting about this one is the fact that they were able to convert everything into dollars. So for triple bottom line, because we're looking at several different topics, it's hard to compare apples and oranges. One approach is to try and put them all as apples. So assign a cost to everything, which is what this study did. And they did it across triple bottom line metrics. So we're looking at human aspects, such as cost to property. We're looking at environmental aspects, such as the costs of flooding and coral reefs and things like that. But we're putting it all in dollar terms. And the other approach in triple bottom line is to just score things on their own terms. So give things scores out of 10 or things like that, or use some kind of multivariate analysis where you're not just looking at everything on one dimension, but you've got some more nuanced decisions and scoring metrics. But this is a really interesting study because it goes through all these different categories and subcategories and assigns dollar amounts to each to be able to compare them. And dollar amounts are the only amounts that some people understand. So I think this is a really great way to visualize how all these effects stack up against each other. So when we're talking about life cycle analysis and triple bottom line, something that comes up in both of these more and more, thankfully, lately is greenhouse gas and climate change impacts. And greenhouse gas and climate change are a big part of why the waste industry is changing the way it is. So we're just going to talk about that metric specifically for a little bit. So if you are a biodegradable, or not even biodegradable, if you are an organic molecule, there are two ways your life can go at the end of life. There's an aerobic pathway where you use oxygen and all your carbon turns into CO2. So that could be for a biodegradable material, it could be composting, or for a non-biodegradable material like a plastic, it could be incineration. It would also end up as CO2. That's one pathway. Our other pathway is an anaerobic pathway. So this typically only applies to biodegradable materials, but instead of using oxygen and getting CO2, we're not going to give them any oxygen. We're going to have a different pathway, and we're going to get a mixture of methane and carbon dioxide. So these are the two paths that materials go in waste management, and both of these are greenhouse gases, right? CO2 is and methane is. But greenhouse gases, they aren't all the same. So the first distinction is different greenhouse gases have different effects in the atmosphere, and that's quantified with a metric called the global warming potential, GWP. And that's usually measured relative to CO2. So CO2 is our most important greenhouse gas. There's the most of it up in the atmosphere, but is one of the lower greenhouse gases in terms of its effects. There's just a lot of it. So methane, according to the most recent science, is about 28 times worse on a mass basis than CO2. And then nitrous oxide is even worse than methane, 265 times. So the waste industry produces a lot of methane in particular because it's a product of landfilling, which is the traditional practice. Everything's buried, there's no oxygen, we're going to produce a lot of methane, and about 5% of greenhouse gas emissions come from the waste sector, largely due to landfill methane emissions. The other way we can talk about greenhouse gases, in addition to their global warming potential, is whether they are fossil greenhouse gases or biogenic greenhouse gases. So just because something is CO2 doesn't necessarily mean in greenhouse gas accounting, it will be counted the same. So if I'm a piece of coal and I get burned and produce CO2, that counts as an emission in any reporting inventory. But if I'm a piece of wood and I get burned, yes, the same CO2 is going to be going up in the atmosphere, but we don't account it the same because that wood is part of a faster cycle that's going on the Earth, whereas the coal will take thousands of years to form. So biogenic CO2 we don't count, but biogenic methane we do count, because that methane in a natural environment, it wouldn't form to the extent that it does in an environment like a landfill. So methane we count whether it's fossil or biogenic. CO2 we only count if it's fossil because a natural system already cycles CO2. And there's strengths and weaknesses to doing the accounting this way. Maybe it's biasing us towards using biofuels that might not be 100% sustainably produced, but that's how greenhouse gas accounting is done these days. And that's a big driver of the way projects are done to reduce greenhouse gases.